My area of research is nuclear structure physics, structure of the nucleus, and I'm primarily interested in the relations between excitations, motions of the nucleus as a whole, thinking of it as an object with a shape or a changing shape as you change the number of protons and neutrons in it on the one hand, and on the other, how those protons and neutrons create that shape, how their interactions lead to those shapes and those kinds of excitations. Nuclear physics is part of the whole field of modern science, and it addresses a number of questions that are of general interest throughout all of science. And the way I like to think of it is in terms of twin perspectives, where on the one hand you have a system with lots of ingredients, particles in it, and they interact. And you try to understand how the interactions of those particles create the properties of the system. And this applies whether it's nuclei or condensed matter systems or biological systems. It's the same theme throughout wide areas of modern science. The flip side of that is to look at the system as a whole. And it will have certain properties, certain symmetries, certain global behavior. And very often, as in the case of nuclei, that behavior is very simple. And nuclei display remarkably simple properties. And trying to find out what those simplicities are, the simple patterns, is one goal, and then trying to understand how those arise from the interactions of the individual constituents is another. And just to give you an example, in a typical atomic nucleus with, say, 100 or 200 protons and neutrons, those protons and neutrons occupy about more than 50% of the volume of the nucleus. They go around in orbits around the nucleus trillions and trillions of times per second. You would think you'd have utter chaos, but you don't. You have very regular patterns of motion, and we try to understand the relations between these two perspectives. For students who are interested in getting into nuclear physics now, I personally think, and I said this recently at a conference, that this is the most exciting time to enter nuclear physics since the late 1960s. I happen to be very old, and I was a graduate student in the 60s, and that was an exciting time because a new generation of accelerators was just coming online, and these were called tandem accelerators, and they revolutionized the nuclear physics of that day. And now we're in a similar revolution where we have these new generations of exotic beam facilities all over the world, which are allowing us to expand the realm or the horizons of nuclei that we can study. And there's a reason why this is important. There are only some less than 300 different isotopes that are stable. There are some 5,000 to 7,000 nuclei that in principle could be studied. I certainly don't want to study all of them, and I don't think anybody else wants to just study all of them. But what they do is they provide a kind of gene pool where we can pick specific nuclei or specific reactions to isolate some physics question that we've never been able before to isolate. And to study that and refine our understanding of nuclei and provide input to theories that will hopefully provide a comprehensive understanding of all nuclei. Our current theories are a kind of patchwork, where we use one theory for one region of nuclei or one type of nucleus, another theory for another region or another type, and that's okay, but it's obviously incomplete. And most of our theories have been built up with data taken with beams and targets that are stable, and that's a very small section or subset of all the nuclei possible. So access to these exotic nuclei provide a tremendously expanded gene pool.